Okay, so welcome everyone to a new PYSQT seminar. Our speaker for today is Lidia Lozano Martín. She did her bachelor's at the Universidad Autónoma de Madrid and then a master at Universitat Politécnica de Catalunya. And she recently started her PhD at the Institute of Cosmos Sciences. And today she's going to explain the beginning of her PhD work. Lidia, whenever you want.
Thank you. So, hello everyone. As said, I am Lidia Lozano Martín, a first-year PhD student in the group of quantum communications in the Universitat de Barcelona. And today I wanted to talk about the goal of our group and the first steps of my research that I've been doing during the past few months. To be precise, I will explain how to observe photon antibunching from localized quantum dots as single emitters. First of all, I would like to introduce our team in the quantum communications group, led by Bruno Juliá, and my two supervisors, José María Gómez and Martí Guido Castella. We have another PhD student, my colleague Raúl, and three interns, Adrià, Sergio, and Núria, whom are a recent addition to the team. And this project is funded by the Next Generation program of Acciones Complementarias. The motivation behind our group are single-photon sources. Single-photon sources are the primary enablers of several quantum technologies, like secure communication based on quantum key distribution, quantum metrology, and quantum sensing, among others. And here you can see some examples of these applications I've just mentioned. However, the development of reliable, robust, and tunable single-photon sources is still in process. Present single-photon and entangled-photon emitters exhibit important challenges, limiting the use in quantum applications. Some of these challenges are directionality, efficiency, or quantum coherence. It is also important to make them robust, so they can be used in extreme environments as space to allow the use for long-distance networks. For that reasons, in our group, we seek to develop a single and entangled photon source for space-ground communications, enhanced by a resonant cavity to direct the photon emission in a particular direction, among other future improvements. In this talk, I will give an introduction on the fundamental topic of my research, that being single-photon sources and the statistics that define them, in particular the antibunching behavior that describes single-photon sources. Then I will explain how can we experimentally measure such antibunching behavior, the antibunching effect. And as the particular single-photon sources we are using, I will talk about colloidal quantum dots and how we work with them in the laboratory. And finally, I will give you a sneak peek of the ideas we have in mind for the imminent future to localize and enhance single-photon sources. So let's begin with the definition of such single-photon sources. A coherent light source, as such of a laser, exhibit Poissonian distribution of the photon emission. That is, the separation between the emitted photons is random. There is the same probability for two photons to be emitted together than with any other temporal separation. However, for a single photon source, the delay between emitted photons is more regularly spaced and unequal. As a result, the probability of having two photons emitted together is significantly reduced, and this behavior is known as antibunching. For a Poissonian distribution in a coherent source, the variance is the same as the mean, but the photon distribution of an antibunched source follows sub-Poissonian statistics, where the photon number variance is less than the mean. So the Poissonian distributions cannot be explained by classical physics. This is a quantum phenomenon because this condition violates the Cauchy-Schwarz inequality, which denotes the non-classical behavior of single photon sources. In a few slides from now, I will show the mathematical demonstration of this quantum phenomenon. Now, imagine a light source that emits photons in any order. If the light is divided by means of a 50-50 beam splitter, the photons follow one path or the other with equal probability. At the end of each path, we place a single photon detector with the capability of detecting singular photons. That is, each click in the detectors denotes the measurement of a single photon. This fairly simple setup is known as the Hanbury Brown and Twiss effect, which is the most common implementation to measure the autocorrelation function of a light source. And it is widely used in quantum correlation experiments, such as ours. If we compare the signal from both detectors, we can measure the temporal delay between the photons detected in one channel and the other. This is the temporal correlation of the signal, and to be precise, is the second order autocorrelation function, G. With this information, we can plot the number of times a particular delay has been counted as a function of the different time delays measured. If we measure the correlation of a source, where, as I said before, of a coherent source, that I said before, the temporal separation of the photons is random, we have the same probability of measuring any temporal delay. In terms of the second order correlation function, it is constant and equal to 1 when normalized. However, if the signal from a single photon source is measured, where the photon distribution is antibunched, in an instant of time, only one count is detected in one channel, and there will not be coincident counts in both detectors simultaneously. That is, we cannot measure a delay equal to 0. In this figure, taken from one of the reference papers that I've used, we can observe the dip at 0 delay time in the second order correlation function for the single photon source they used. And this is the behavior that demonstrates the emission of a single photon source. And the antibunching effect we aim to measure, where the probability to measure two photons simultaneously is significantly suppressed. Now, don't fret, because this is the only slide with equations, and I will try to make it as bearable as possible. So for a more formal analysis of the second order correlation function, it can be written in terms of the creation and annihilation operators, as shown. This gives information of the photon statistics. The correlation is a function of the delay between photon detection, as I explained, but it gives the probability of detecting two photons with a particular delay, tau, and the degree of coherence for the photon coincidence rate. For a 0 delay time, the correlation function is simplified, as shown, and it can be written in terms of the number of photons. If the source exhibits antibunching, where the variance is less than the mean, for a 0 delay time, the correlation is less than 1, ideally 0, and less than at any other given delay. That is, to repeat, the probability of detecting two photons at the same time is significantly suppressed. From this inequality follows this relation, and as I previously mentioned, it violates the Cauchy-Schwarz inequality, which is one of the most important inequalities in mathematics, which denotes the non-classical behavior of single photon sources in the mathematical description of the effect. Now that the fundamental introduction of the subject has been explained, I'm going to talk about the experimental work I have been doing in the laboratory to characterize single photon sources. My work during my master thesis has been dedicated to set up an accessible optical system to measure antibunching behavior by means of the Hanbury Brown and Twiss effect I have explained. And this experiment is intended to be used by undergraduate and master students in the next course for them to get in touch with the experimental measurement of light coherence. Now I will explain with some detail the optical setup to characterize single-photon sources. As the excitation light, I have used a blue laser, and in this part of the setup, the laser beam is collimated and cleaned. Then we have a fluorescence cube, which is the same system of filters used in fluorescence microscopy. So the blue light is reflected and focalized onto the sample. And the single photon sources, when excited, they exhibit fluorescence. In our case, it's red fluorescence. The light emitted by the single photon sources is collected back on the system and transmitted to the next part. Here I have set a removable mirror, and when the mirror is placed, the fluorescence light arrives to the camera, which allows me to observe and scan the sample to look for the single photon sources. Once I have located one of the single photon sources, the mirror is removed. Now the light can arrive the Hanbury Brown and Twiss part of the setup that once again, I'll repeat, when a photon arrives to the beam splitter, it follows one path or the other with equal probability, and only one photon is detected at a given time when we have a single photon source. The signal from the detector is then analyzed and the correlation is performed. So when a photon arrives to the channel 1, we measure the delay between that detection and the other in channel 2. With this information, we can plot a histogram of the number of times a particular delay has been counted as a function of the different time delays measured. We have successfully measured the second-order correlation function of a coherent light source, in this case, the blue laser light of the excitation, and as expected, is constant, and where normalized is equal to 1. Now, obviously, the next step is to measure the emission of a single photon source. An ideal single photon source behaves as a two-level system, and a real example of two-level systems are quantum dots. Quantum dots are semiconductor nanocrystals that, due to the quantum confinement in the 3 dimensions, they have discrete energy levels as such of an atom. That is why they are commonly known as artificial atoms. We are particularly interested in colloidal quantum dots, as they are semiconductors nanocrystals whose optical and electronic properties promise to be beneficial for our goals. And in addition, the wavelength can be tuned by changing the size of the core of the quantum dots. Moreover, antibunching behavior has been largely observed in quantum dots. In particular, we are using core shell, cadmium, selenide, zinc sulfide quantum dots because the shell has been proven to stabilize the photon emission, increase the intensity, and avoid photobleaching, which is the complete cease of fluorescence due to external damage. In addition, they are carboxylic acid functionalized to avoid clusterization, which is the formation of clusters, which is the aggregation of the quantum dots. These quantum dots have a narrow emission in the red regime, in particular in 620 nanometers, as you can see in this photoluminescent spectrum. And they have a broad absorption in the blue-green regime, optimized in around 450 nanometers, and that's why I chose that wavelength for the laser emission. We performed some experiments to determine the morphology and the degree of clusterization of the quantum dots, depending on the time and temperature during the sample preparation. In these images, taken with transmission electron microscopy, we determined that the core size is around 6 nanometers, and that if the evaporation of the sample is relatively fast, around 30 minutes, the quantum dot samples can be prepared at room temperature and they don't exhibit clusterization, which can be easily done by the future students. And these are quite interesting images because we can clearly see the crystal structure of the quantum dots. And in particular, we can see the atom chains, which I find quite fascinating. Now, in this video, we can see the Brownian movement of one of our colloidal quantum dots in the water mixture they are kept, which brings us to the next challenge. To successfully measure the single photon emission, we need to isolate a single quantum dot, which in theory could be achieved by reducing the sample concentration. However, we are particularly interested in a method to easily localize the position of the quantum dots in the sample for further fabrication of the structures. If we don't have a single photon source, and we have a lot of quantum dots, as you can see in this sample, antibunching cannot be observed. And what we can see in this autocorrelation function is thousands of single photon sources emitted at the same time, and we cannot see the antibunching dip. So this takes us to the upcoming steps of my research, which is finding a technique to isolate and localize single photon sources. We are currently trying different methods to isolate and localize colloidal quantum dots. The most promising one for now is to coat the substrate with a PDMS layer, which is a hydrophobic elastomer. And once the coating is done, we have fabricated holes on the PDMS layer with a pulse laser, which allows us a controlled design and size of such holes. As the mixture of colloidal quantum dots is in water, these holes are more hydrophilic and energetically favorable for the water to drop inside. Once the holes are fabricated, we place the colloidal mixture with the quantum dots in water on the sample. If the concentration of the quantum dots is such that statistically there is only one quantum dot per hole, we can have a method to isolate and localize quantum dots. In this sample, where I fabricated these 15 microns holes, we can clearly see the red fluorescence from the quantum dots only inside the hydrophilic rectangles. And that's a success. The next step is to reduce the size of the holes and get the same result. However, the reduction of the hole size presents some challenges, as the water surface tension is very high and the air inside the holes also blocks the water. For now, we are focusing on reducing the thickness of the PDMS layer coated on the substrate to reduce this effect of the surface tension and the volume of the air trapped inside the holes. Once the localization of the quantum dots is completed, we will move to my personal favorite part of the project, which is the submicron fabrication. We have a nanoprinter that allow us to build 3D structures with a resolution of 200 nanometers. And here we can see scanning electron images of some of the structures we can fabricate, and a video that I will play again of the device during printing. And I could have shown you the printing of one of the resonant cavities, but I think the dinosaur is more fun. And the resonant cavities are too small to be clearly observed. And for you to get an idea, this dinosaur is 100 microns, and the last structure I fabricated was less than 10 microns. So to appreciate the small feature, it needs to be observed with the scanning electron microscope. Now, one of the initial structures we plan to characterize to enhance the photon emission are Bragg reflectors. spherical Bragg resonators seems to be a good candidate to direct the photon emission, as these reflectors consist of distributed layers where the index of refraction is periodically alternated. The phase matching condition for resonance is fulfilled when each layer has a quarter wavelength of thickness. And our goal is to fabricate and characterize resonant cavities and other structures around the quantum dots to control and direct the photon emission. And here we can see a spherical Bragg resonator I have designed and printed, as well as the numerical simulation of the light emission expected to be observed if we place a quantum dot in the center of the cavity. So the next step is to fabricate these structures around the quantum dots and characterize the photon emission. So that's all for my presentation, and I hope you enjoy it. And on behalf of my team and myself, thank you very much for your attention and for letting me participate in this seminar.
Okay, thanks, Lidia. Let's see if there are questions. Okay, maybe you can keep the presentation open.
Oh, yes, wait. How was it? Oops, one sec.
Yes, I have one question.
Yes.
Just for maybe targeted as for everyone in the audience not so familiar with quantum optics, why would you be interested in creating single photon sources? I mean, why in general would that be interesting or practical for?
Let me give you some of the initial examples of the application of single photon sources. Wait. Okay. So single photon sources are used in quantum technologies, and they are now the fabrication of, as I said, this robust and controlled single photon sources is not quite yet, and it's single photon sources are used in many quantum technologies. For example, the most used examples is the quantum key distribution, where we can encode information in one photon, and we can use it to encrypt information and to keep secure communication and have secure communication, which is the goal of our project, to fabricate such device to be used in quantum key distribution and quantum telecommunication technologies to secure the information encoded in qubits, which will be in this case photons, single photons.
Okay, thank you.
So I have another question, which is about how advanced is the project. You discussed an optical setup with your laser source that you then focus on the single photon source. This one. And you showed some, I think, some experimental results for the coherent light source. But have you done the experiment as well with single photon sources or not?
As we have not yet isolated a single one,
okay,
we have not observed the antibunching, and that's where we are now in this process to isolate a single photon source and to measure successfully this antibunching behavior. We have measured the coherent laser source of the coherence of the laser, and we have tried other samples with the quantum dots, but as we have yet not get the technique to isolate them, the antibunching has not been performed. but the system works as expected and the correlation is done correctly. Yes.
Okay, and you explained that you have this removable mirror to
Yep.
then deflect the light towards the camera and be able to focus on your sample. What would you be changing in order to locate your single photon source whenever you have it? Do you just move the plate with the sample, or?
Yes, that's one of the troubles of the challenges we are having now, because quantum dots are really small, 6 nanometer size, and it's hard to locate them in this optical system. So we place the sample with the quantum dots in a stage system, and then we can scan the sample and observe the fluorescence in the camera as if it were a confocal microscope. And this experiment usually is done using a confocal microscope, which has a lot more precision. But our idea is to build this optical setup, which is basically this part of the setup is like an open fluorescent microscope for the students to touch and clearly see the optical elements of the acquisition of the system. And yes, so with the removable mirror, we can have these two separate systems. When we have the mirror, we observe image of the sample, and when we remove the mirror, we can perform the autocorrelation. And we are still working on some improvements on the setup. Actually, the camera, it's a relatively recent improvement, and the stage system could be motorized to have more precision of the scanning of the sample.
Okay. So, you have mentioned students a few times, so it seems to me that you are at the same time trying to build a state-of-the-art experimental setup and an educational experiment for bachelor students or something.
Yes, this experiment is going to be part of the quantum laboratory of the quantum and technology master. Wait, I don't know how to say that in English. The quantum and quantum technologies master in the Universitat de Barcelona. They are trying now to open this subject of the experimental to have a experimental subject of in the master, and we are working on several experiments for them to be used for the students. And we have the Bell inequalities measurement one, and this is the other we have. And in the next month, they are going to bring other experiments for the students to use next year.
Okay, but this is also like part of a scientific project just for the sake of science, or is
Yes,
it only
so,
educational?
No, it's twofold.
Okay.
Like, we have this setup that is going to be used in the quantum master and for undergraduate students also. And at the same time, we are going to reproduce this setup with more precise equipment. We are going to reproduce this exact same setup to characterize the single photon sources we are developing in the group of the quantum communication. So this was my first approach on the sample during my master thesis.
Mm-hmm.
And now I'm still working on this optical setup to improve it and to have an actual optical system to characterize the single photon sources we are developing.
Okay. Okay. And then I think one last question from me. You explained this technique of punching holes in this hydrophobic substrate, and then depositing some solution with the single photon sources with the quantum dots. At some point, you showed that it worked, but then you needed to make the holes smaller, and if you made them smaller, then it didn't work because of surface tension. Why
Yeah,
do you need to make them even smaller?
it's because of the future fabrication of the structures. If these holes are too big, then the structures we are going to do with the nano printer are going to be inside the hole, and maybe it would be more interesting to build them on top of the PDMS layer. So that's one of the reasons for the future structures, and to see if we can make the holes smaller. Another reason is because if the holes are smaller and we have the correct concentration of quantum dots, is statistically more probable to only have one quantum dot per hole. What happened in these bigger holes is, even though the concentration of the quantum dots was small, we had several quantum dots in the holes. That is what we can see in these samples. If we make the holes smaller, we could have less probability of having more than one quantum dot per hole.
Okay. Okay. Well, I don't think there are any other questions. So in that case, thanks a lot, Lidia, for your talk. I think it was very accessible. And yeah, thanks everyone for attending.
Thank you very much.
Thank you.
Very informative indeed.
Thank you all.